Good day. The topic is pile foundations. So for the definition, piles are structural members that are made of steel, concrete, or timber as replacement for shallow foundations. So for sample applications, for the first figure, pile supports the superstructure that is high-rise building. And for the second figure, pile supports the bridge. What are the two purposes of pile foundations? First is to transmit a superstructure load to deeper load-bearing strata, and second, to withstand lateral, vertical, uplift load, and to minimize the settlement. So why piles are needed? First, top layers of soil are highly compressible for it to support structural loads through shallow foundations, especially if the soil carrying capacity cannot sustain the imposed load, so which results to settlement. Second, rock level is shallow enough for end bearing. Pile foundations provide a more economical design. So if rock level is shallow, so we do not need a very long pile and might be more economical than over-designed shallow foundation. Third, lateral forces are relatively prominent, such as earthquake. Fourth, in presence of expansive and collapsible soils at the site, so expansive soils are clayey soil, and collapsible soils are soils with very large volume of voids, such as honeycomb structured soil. Fifth, offshore structures. So these structures, such as bridge, piers, and structures built on or near bodies of water. 6. Strong uplift forces on shallow foundations due to shallow water table can be partly transmitted to piles. So uplift forces may push the shallow foundations or footing, thus piles are built and injected at deeper strata. And for the 7th, for structures near flowing water, such as bridges, abutments, etc., to avoid the problems due to erosion. So piles also act as retaining structures. We have 4 major classification of piles based on materials or composition. First is steel piles. So for steel piles, it is either pipe or tubular piles, or the rolled steel H-section piles. Second is concrete piles. So under this classification, we have precast that is either circular or square-shaped piles. So these are pre-ordered or pre-manufactured piles. While another is the board cast in situ pile. So for the third is timber piles. And for the last, it is the composite piles. So for the composite piles, it is the combination of the first 3 classification of piles. Again, steel, concrete, and timber. So for the 2 classification of piles based on the nature of their placement, so are the following. So first is the displacement piles. So driven piles are displacement piles because they move soil laterally. Hence, there is a tendency for densification of soil surrounding them. So densification or otherwise compaction process. So concrete piles and closed-ended piles are high displacement piles. So displacement or driven piles are installed or injected through the soil by means of vibration or impact hammers as presented in figure 3.10 and with the actual equipment with figure 3.11. So second is the non-displacement piles. So board piles are non-displacement piles because their placement causes very little change in the state of stress in the soil. So for these piles, the process is to drill a vertical hole as presented in figure 3.12. So, drilled to the desired depth. So, once the hole is drilled, the reinforcing steel bar is built and lowered into the hole. Then, it will be filled with concrete. So, the top of the pile may be capped with footing or air. So, as presented in figures 3.12 and 3.13. So, for the types of piles based on their function, so first is the point-bearing piles. So, it is dependent only on rock layer at the tip or end of the pile. So, thus, the capacity is only the bearing capacity at the tip of our pile. So, another is instead of bedrock or presented at the previous slide, so piles can be extended through a strong soil layer. So thus, the capacity may be expressed as, so our QU, the ultimate, is equal to the point bearing, so at the tip, plus the skin friction, so at the side of the pile. So second is the friction piles. So no layer of rock or strong soil, thus it is dependent on the friction between the pile and soil. So for this type, may require longer piles or piles with large surface area, because again, it is dependent on the friction between the side of the pile and the soil. So last is the compaction piles. So it is intended for compacting granular soils. So for the length of these compaction piles, so it is dependent on the following factors. A, the relative density of the soil between compaction. B, the desired relative density of the soil after compaction. And C, the required depth of compaction. So these piles are generally short. However, some field tests are necessary to determine a reasonable length. Again, to satisfy our different factors. So for the equations now for estimating the pile capacity, so the ultimate load carrying capacity, QU, of a pile is given by the equation, again, as presented earlier, with our different types based on their function. Okay, so for our QU is equal to the QP. Again, this is the point bearing. So the bearing of, or the bearing capacity of the soil which is directly in contact with the base of the pile, plus QS. So QS is the frictional resistance or the skin friction, so derived from the soil-pile interface. Or it is the friction between now the side of the pile with the soil. So this is our QS, and at the tip is our QP. So, and in addition, for our diagram, we have our Q prime. Again, Q prime is, or Q is the overburden pressure or surcharge. So, with vertical effective stress concept, thus Q is equal to gamma prime times Z, where Z is the length of the pile. So for our pile case, that is now Q is equal to the gamma prime, multiply that with Z, that is L. So which is related to our discussion of shallow foundation, that is the Q is equal to gamma times dF for the depth of footing. For this case, our depth of footing is the length of the pile. So for the steel piles, so we have now again our pipe pile and our H section pile. So for our pipe pile, for the area, we will consider the area of the steel together with the soil plug. So the soil portion in between. So Similarly, for each pile section, we will consider this as one big rectangular area. So we will consider the portion inside now these broken lines, which are the soil plug portion. So therefore, for our pipe pile, we will consider the area as a full solid circle, while for each pile section, we will consider that as rectangular section. So let's have now the overview of the components of our ultimate capacity. First is the point bearing load capacity Q sub P, or capital Q sub P. So the ultimate bearing capacity of soil considering general bearing capacity equation. So shape, inclination, and depth factors are included in bearing capacity factors. So our bearing capacity factors now are NC star, NQ star, and N gamma star. So our QU, which is from the concept of shallow foundation, will be our Q sub P for our point bearing. So since pile diameter is relatively small, therefore the third term may be dropped. So our B gamma N gamma star. Thus, our QU, which is our QP now, so our small QP, is equal to C prime N star plus Q prime NQ star. So thus, the point bearing load capacity of pile is, so our capital Q sub P is equal to our pressure QP times AP, our area of the pile. So AP again is the area of the pipe or our rectangular or square section pile. Okay, C prime is the cohesion of the soil supporting the pile tip. Again, for point bearing load, we will consider the parameters that is directly in contact with the tip of the pile. So for QP, the unit point resistance, again this is the pressure capacity. So for Q prime, so the effective vertical stress at level of pile tip. Again, this is our gamma times DF or gamma times L. So NC star and NQ star are the bearing capacity factors. So on the other hand, for the second, we have the frictional resistance Q sub S, so capital Q sub S. So the frictional or skin resistance of a pile may be written as, so Qs is equal to the summation of P times delta L times F, wherein P is the perimeter of the pile section, delta L is the incremental pile length over which P and F are taken to be constant, and F is the unit friction resistance at any depth Z. So for this, since we are dealing with frictional resistance, again, this is the skin friction of the wall or the pipe wall, or the pile wall rather, together with the soil. So therefore, we need to consider the surface area, which is our P multiplied that with our L. So the perimeter multiplied with the length. On the other hand, the allowable load Q or capital Q sub all is equal to our ultimate capacity QU, the combination of QP and QS, divided by the factor of safety that ranges from 2.5 to 4. So unlike for the shallow foundation, the factor of safety is about 3 for conservative condition, while for this pile, the range of the factor of safety is about 2.5 to 4. Okay, so that's it for pile foundations with the general concept of piles. Take care and God bless.